Hello, this is just a quick video introducing the GraphViz tool as well as the web version and how it'll help you with your binary search tree assignment, specifically with debugging. So getting right into it, you should be able to see under the modules for week 9 alongside everything else, this using GraphViz in this the dot format files. So if you go ahead and open up using GraphViz, it's a little introduction. GraphViz is a really cool tool that helps programmers to visualize graphs. It does it in a really neat way where it just basically needs a string. Technically, it uses a specialized file called a dot file, but that is just a glorified text file. So in other words, it's just a string. So the GraphViz tool is a standalone program that you can download and use. There's some information here on how to use it on Windows, Linux, or Mac. However, it is a little more difficult than is necessary because there is a web version. So if you go to this GraphViz, come up to the URL and just type in web and replace the org with a com. It'll open up this web GraphViz, which is a GraphViz in the browser. Alternatively, if you go to Piazza, there should be an announcement mentioning this www.webgraphviz.com. Again, opening it up, it'll take you to that same place. As far as what GraphViz does, if you open up, you can also see this page or just open up the dot format directly. It talks a little bit about what WebGraphViz and GraphViz themselves take in. The specialized dot format is essentially a very syntactically important language that the GraphViz tool / WebGraphViz tool can take in to create a nice visualization of graphs. For example, here, when you first open it up, it has a very simple one. So this is like digraph G, and then it has an open close curly braces. Welcome, point 2, 2 point web, 2 point GraphViz. Well, if you click generate graph, it makes a lot of sense. Welcome points at 2, 2 points at web, and GraphViz. Really neat. There's a bunch of samples here, all of which show a little bit more about how deep this can go. So, for example, this one showcases how you can encircle things, create groupings of things, make some nodes more specialized. Sample 2 gets really into it with the specialized node styles. Sample 3 gets really into just how big and complicated you can go ahead and make these graphs. It's all really neat. However, for our use cases, we don't need to make anything nearly that big and complicated. Here, all we want to do is create a nice visualization of our binary search trees. So to do that, we have given you a bit of demo code again from that using GraphViz page. If you download it, I already have and import it into Eclipse. It has these two files, this binary search bst.java file and bstdemo.java. You'll notice this bst.java file is actually kind of a nice starting point for your own binary search tree, but that's beside the point. What we're interested right now is in these final two methods called write.dot and write.dot recursive. And the binary search tree demo just creates a basic binary search tree, runs a few contains methods. We can go ahead and comment those out because they're not very necessary to us right now, and then calls that write.dot file. So looking at our write.dot file. Our write.dot takes in a file name, so it's where it's going to end up storing this .dot file. And then it needs to be enclosed in a try and catch, because anytime you're doing anything I/O, it needs a try catch. Anytime I/O exceptions can be had, you want to deal with them. Everything that I/O is going to throw exceptions if it can't access it or doesn't have permission, what have you. Either way, it creates this new print writer based on a file writer that takes in that file name. So essentially, it just creates a new fancy writer out to that file name that you've given it. It prints out this digraph BST and a specialized essentially a specialized line that just tells the GraphViz tool what our nodes are going to look like. So you notice that here it says digraph, which means every node is going to be directioned. It's going to have an arrow. Alternatively, if you just said graph here and changed a little bit down here, instead of arrows, it would just be straight lines connecting, but binary search trees are directional, right? Every node points to its two children nodes. So we want it to be directional, and then we have a named binary search tree, and then our opening brace. Eventually we'll print in our closing brace to enclose this binary search tree. Again, explaining what the node's going to look like, and then as long as we have a root in this binary search tree, we're going to go ahead and call our recursive method on that root, passing in this file writer / print writer all the way down so that it can be used by every single recursive call. Recursive call itself, if you'll notice, has a very similar structure to a pre-order sort, or pre-order traversal, sorry. It handles the current node, and then if there's a left child, it does something with the left child. If there's a right child, it does something with the right child. A pre-order traversal. There's a small edit in the fact that after it handles the child, it does a little bit more, but that's still technically working with the left child. So as far as what this is doing, it's going to print to our output file another specialized bit of information that just says, all right, we want the node, our current node, to look like this and have a left child and a right child with some fancy lines to make it look pretty. And then if the left child exists, it's going to work on that left child, i.e. if the left child exists, it'll immediately come back up here and say, okay, well, this node is also going to look pretty and such. And then once that's finished, it'll come back out and say, sorry, it'll say, okay, go ahead and add that left child as a child of this node. Exactly how that's doing that, you don't have to worry yourself too much over. You can study that up later, but that is what this program is doing. You will note that this binary search tree file is specialized in the fact that it is only of type string. Each of the nodes contains a string piece of data right here. So in order to, if you want to use this in your own binary search tree, you'll have to edit this slightly so that instead of just being able to append n.data here, you'll have to append the string version of node.data or n.data. So however you're handling that in your generic case should be fine. We then have this binary search tree demo file, which essentially just again creates that binary search tree and calls that right dot. So right now, you'll see that it has this question, what happens if the items are inserted to a binary search tree in ascending order? Well, we're creating a binary search tree and inserting these words: alpaca, cat, chupacabra, cow, dog, dragon, pelican, zebra. After these are all inserted, we create that right dot file. So if we just go ahead and run this, you'll notice that these are in that ascending order. It'll create the file. For most of you, depending on how your Eclipse works, it looks like nothing will happen. If you go ahead and right-click just about anywhere inside of your package explorer, preferably just the highest package that you have open right now, and click the, where'd it go? Refresh button, it should show up down here at the bottom for me. Alternatively, you can just hit F5 and it'll show up. But if we open it up, a .dot file in most computers, most Windows computers, is claimed by Word by default. So it may try and open it up in Word. It should be fine if it does. It shouldn't cause too much of an issue for you. But alternatively, if you go ahead and hit open with and just a text editor, for example, that Eclipse has inherently, it'll open up whatever your basic text editor. Here I'm using Notepad. And bam, it makes this really complicated looking file. However, we can see kind of what happened. We have our digraph BST, that special instruction that says what our nodes are going to look like. And then there seems to be a distinct difference between this chunk of information right here and this chunk of information. You can see that these are all of the pre-order traversal going through every single node and stating that it's going to look like this specialized node we were talking about earlier. And then it goes through and actually connects these nodes using these, again, these arrows. It connects pelican, and it's saying the right is the zebra going down. And this is a little more complicated than you have to worry about right now. But if you go ahead and just take that, copy that file, come back to that web GraphViz, paste it in, and click Generate Graph, you'll see that makes a really nice graph of what we just had: alpaca, cat, chupacabra, cow, dog, dragon, pelican, zebra. However, like we said, we're adding them all in ascending order. And so every time we add one, it's always going to end up to the right of whatever was last added, right? Because cat is quote unquote greater than alpaca. It comes later in lexicographical ordering. And so everything is on the right child. And you'll see that that's our specialized node structure, right? It shows the left child and the right child. So alternatively, if we come back to our, binary search tree demo, there we go. And if we just shuffle it around a little bit, it's like we take cat and we insert it at the very end. We take pelican and we insert it where cat was inserted. We take cow and we insert it where pelican was inserted. We can take alpaca and insert it where I think pelican was inserted, right? Or whatever case may be. We just kind of sprinkle it around a little bit. That should be good. So that's a little more shuffled, right? So then if we add it to our binary search tree, it should look a little bit different. So if we go ahead and run this again, it'll output to the same file, so it won't create a new one or anything. If you already had it open, it'll be, most of your text editors are like, hey, this changed somehow. Totally fine. It changed it a little bit. Again, you don't have to worry too much about what this looks like per se, But if you come into that web graph viz and paste it in, click generate graph, bam, we have a lot more balanced, more or less, looking binary search tree. Pelican's left child is chupacabra, chupacabra's right child is dog, dog's left child is cow, yada yada. Pelican is greater than zebra, chupacabra is less than pelican. Alpaca is less than chupacabra, dog's greater than chupacabra. Cat's greater than alpaca, cow is less than dog, dragon's greater than dragon's greater than dog. It follows our insertion just fine, and it has a nice little visual representation. So when it comes to debugging, if you go ahead and implement this code right here in some way, shape, or form to create these .file outputs, it'll make it way easier for you to quickly just throw that file, or throw that string, right, the file technically, into this web graph viz and to very visually see what your graphs actually look like, what your binary search trees actually look like, and have a very quick indication of, okay, yes, everything got connected correctly, or for example, if everything is a right child of the last thing, even though some things were less than other things, you obviously had an issue. So it's just a really helpful tool to quickly verify that your binary search tree got set up correctly. Other than that, it's not necessary for the assignment, so if you don't want to use it, you're totally fine, but it is very helpful for debugging. Other than that, as per usual, if you have trouble with this web graph viz or technically the GraphViz in general, not all of us TA have actually used the GraphViz standalone tool. Web GraphViz is totally fine for exactly what we're using. But if you have questions about any of that, please post on Piazza, come into TA hours, whatever have you. We'll be happy to help you out with that. Otherwise, best of luck on the binary search tree assignment. Hope it goes well, and thanks.